All right, hello. I'm Stephen Newberry. I am presenting my Project 1 slides for ECE 504, spring 2023. I named my project TLNN for Transmission Line Neural Net. So to give some introduction and some theory here, we're looking to obtain characteristic impedance and electrical length for transmission lines, and obviously this is important. This is important for RF design, especially electrical length and characteristic impedance, and then for high-speed digital design, this can be especially important, maybe more the characteristic impedance than electrical length per se. And traditionally, the way this is done is using a field solver, whether that's a 2D field solver to get your transmission line characteristic, or a 3D solver for full wave three-dimensional discontinuities. Traditional field solvers can be costly, very expensive to get licenses for, and they can be slow. Now, the caveat here is that this problem set we're looking at is 2D transmission lines, the uniform cross-section here, and those 2D solvers are not necessarily slow. Their speed isn't really a hindrance to design, but at the same time, having an opportunity to speed them up would be excellent. So these problems are perfect for machine learning. A little bit of basic transmission line theory. We're going to specifically look at printed circuit board, planar geometries, packages, things like that. So we're going to need to have an understanding of the trace geometry. So we're going to look at microstrip trace. This is going to have a reference plane, it's going to have a dielectric, and then a signal trace above it. This transmission line has a characteristic impedance, and it has an electrical length. So that characteristic impedance is based upon the cross-section. It's an instantaneous property of the line. So a signal propagating down the transmission line will see that impedance as it propagates. It's mostly a function of the parasitic capacitance and the inductance of the line. So that means that the characteristic impedance is very easy to compute from RLGC parameters. So from Posar's book there, it's essentially a square root of L over C, but if you take into account the resistance and the conductance, you get a little bit of a more accurate equation. There are some factors that impact characteristic impedance in terms of the physical design. So the dielectric thickness has a major impact. The dielectric material, which has its dk or df, also known as permittivity and loss tangent. This is driven by things like the resin content, the glass content, if it's a FR4 fiberglass weave or whatever other material might be used. Copper roughness actually does have an impact on characteristic impedance because of the fact that parasitic capacitance causes a increase in the effective dielectric constant. So if you read Bert Simonovich, he talks a lot about that property, that phenomena. The copper thickness does have an effect on characteristic impedance. If you use a thicker signal trace, you're going to have slightly higher capacitance value, so a little bit lower impedance. Etch factor, if you have a rectangular cross-section on your trace, or if you have some etch back, causing your trace to be slightly trapezoidal, that will increase the impedance. And then also, if your microstrip is coated with, say, a solder mask, a molding compound, or some sort of underfill, that's also going to affect the impedance. Characteristic impedance is also notably variable over frequency. So I've got a plot here of some specific transmission line, and it's at 50.8 ohms at 1 gigahertz, but that varies as the frequency changes. Also notable, the characteristic impedance isn't dependent on physical length at all. Now, a quick note on this project, everything I've done today is at 1 gigahertz. The electrical length, essentially similar to the unwrapped phase of the transmission line, is a measure of how many wavelengths long the transmission line is. We're going to measure it in degrees today, and that wavelength is interestingly, it's dependent on the permittivity, right? So that's going to affect the speed of propagation. There's a little bit of nuance with a microstrip here because the dielectric above is different from the dielectric below. So as a result, the effective decay is different. In this equation from Posar's book, you wouldn't use the permittivity of the dielectric material under the trace. You would need to use the effective dielectric constant. So the reason this is important for this particular project is that we can't just extrapolate straight from physical length to electrical length. We could do something like that in a strip line trace, but in a microstrip like this, we have to account for the trace width because the trace width will affect the effective dielectric constant. So what's the motivation of using machine learning? Field solvers exist: Cadence, Ansys, Symbior, Keysight. There are many commercial offerings for field solvers, but they can be slow, like I was mentioning, especially if you have something very large design, hundreds of nets, very high complexity, maybe very small feature sizes down to the micron feature level feature sizes. It can take days to simulate. Now these two-dimensional transmission line solvers can be very fast, but even in the 2D example, some literature noted here, some of the work that I've done with Dr. Zedigal, we did a 2D transmission line solver that used a neural net, and we achieved a 14x speed up. And then we did a arbitrary 3D solver with one particular via geometry, and we achieved 6,500 times speed up over ANSYS HFSS. Now, those speed up numbers don't account for the model training time, and these works were by no means refined. There's a lot of work to be done, but you can see in the plots at the right, I have a insertion loss and return loss plot on the top, and then a TDR plot on the bottom. This is from reference 5 there, the 3D solver. I was shocked that we can take a neural net and we can generate S parameters and look at results that are extremely similar to what you would get out of a traditional Maxwell's equation-based field solver. So it's an excellent application. I think it's really, machine learning is something that can continue to be explored in the area of electromagnetics and hopefully improve design cycle times significantly. A little bit more literature review, like I was saying, 2D solvers. I have my own work here. The plot on the right, on the top, is a comparison of characteristic impedance calculated from a field solver versus a machine learning model. That's the blue and the green curves, and they overlay pretty well for that example. Now, one caveat with that work is that as you got towards the bounds of the training data, upper bound and lower bound of the input feature sizes, you really saw performance drop off. And in that case, the situation was using 5 input variables. We were doing trace width, trace height, dielectric thickness, as well as DK and DF. There's another example of some work, reference 6 there, using a coplanar waveguide for RF as well for 2D. In the 3D space, there's not very much that I found that was specific about with regards to electromagnetics for interconnect design per se. Maybe there's more in the area of antennas or human body model things, radar cross-section, things like that. But in the area of planar interconnects, there's the work that I did over here showing how I was meshing the model, because that work was interesting because instead of using parameters like here's the via diameter, here's the trace width, here's the via length, or here's the distance to stitching via. Instead of doing that, this work, reference 5, took a via, many different iterations with different geometries, but then the system would mesh into dielectric or signal or reference metal, 3 different options there, and the input to the neural net was only that mesh. So the neural net had no concept of a diameter or a trace width. It only knew what material was at what particular location in the geometry. So that was very interesting. I'm really excited to continue working on that area. Like I was saying, when it comes to parameterized structures, there's quite a few references, examples of work using parameterized structures. They would input things like via diameter or trace width or anti-pad diameter or substrate thickness or things like that, and those can achieve pretty good results as well, but just a different approach. Now here's the methodology that I used for this particular project. Everything is in a Jupyter notebook, and to start out with, I set up my notebook, I configured logging, configured the field solver SDK that I used. I'll go into that in a second. Quick note about units. All of my units of length are in mils, 1 mil being 1,000th of 1 inch. That's very common for printed circuit board design. So for the substrate thicknesses, transmission line lengths, and such. So the first thing we're going to do, we're going to create the substrate. Now, I used a field solver called Symbior. This is a commercial tool used in industry, and there's a reason I chose it. First of all, it's very, very fast. In terms of its 2D field solving capabilities. Now it's not using an equation-based, analytical-based approach. It's using a solver. They call it the SFS solver. I believe it's a either a boundary element method or a method of moments type of solver for 2D transmission lines. Also, it has a Python API, which is excellent to use, and it makes it very easy and quick to generate large data sets, and it's also very accurate. So we created the substrate here in Symbior. Now I've got an image of the substrate, but all of this was done in the Python code, not in the GUI. We're doing an uncoated microstrip. For the dielectric material, I chose an Isola PCB material called FR408HR. This is a common material used in medium speed digital designs. You're not going to get up, once you get beyond maybe 8 gigabits per second, there are better materials to choose, but it's pretty common and below that. In this case, I chose a 2x3313 weave with 55% resin content and an 8 mil thickness. So this is one of the core material from Isola that you can get off the shelf. And that particular construction has a DK value of 3.68 and a DF of 0.0087 at 1 gigahertz. Now I did not model any roughness or any etchback. We're just using a smooth copper rectangular cross section. And copper conductivity used the textbook value 58 times 10 to the 6th Siemens per meter. So here in this first section of the code, I configured the substrate parameters. I initialized the project. The frequency sweep, it wasn't a sweep. I did a single 1 gigahertz point, generated the materials. Also important to note, this project uses a wideband Debye causal dielectric model rather than a flat non-causal model. Now that may not particularly have an impact on today's project, but if you were going to do wideband work, you would want to make sure that your frequency, your dielectric model is frequency dependent for causality. And then in this section of code, I created the 2-layer substrate. The reference layer thickness is unimportant at this geometry, but the trace thickness is. Next, in the field solver function, I generated a function called simulate t-line. It takes width and length as its input, and as a result, it outputs characteristic impedance, electrical length, and execution time, so I could get an idea of how long it was taking to simulate these things. With this, we generate the transmission line, we generate the results using the SFS method of moments quasi-static field solver, and then the phase constant in radians per meter was converted to this electrical length in degrees, and that is based on the input length for this function. Next, in the code, I went and did a quick test on the field solver function. So I input a width of 16, according to Eric Bogatin. His rule number 27, which is that a 50 ohm microstrip is going to be roughly, you want to use a trace width that's roughly twice the dielectric height. So I'm using an 8 mil dielectric. So a 16 mil trace width, and I used 10 inches or 10,000 mils as the length. Now this executed in 1.34 milliseconds using the field solver, and it results in an impedance of 51.97 ohms, which is pretty close to the rule of thumb, and an electrical length of 515 degrees. Excuse me. Now the expectation was that it would be 50 ohm, and it was pretty close. And then using the equation from one of our previous slides, we can try to compute the approximate electrical length. So if dielectric, the effective dielectric constant is 2.85, that's according to reference number 10 here at the end of the slides. We get a wavelength of about 7 inches, and we're using a 10-inch trace, so 10 over 7 times the 360 degrees, we get 514.5. So we know that the simulation function is doing pretty much what we expect. All right, so moving on. We needed to generate the training data. So I have a Boolean generate new training data, which I set to true when I'm running it, and then false otherwise, so I don't accidentally regenerate training data when I run the notebook. We'll configure the number of points. Now for my example here, I generated 1 million points, hoping that having a very high number of data points was going to help. I generated a timestamp to track different versions of the data. Now, probability distribution. All of the references that I show of previous work that I've done has used a uniform probability distribution. But in this case, I decided to use a log normal. And the reason for that is I wanted to really center the data around most common feature sizes used. So for example, maybe in this case, we're looking at a PCB, maybe roughly mean length of 6 inches, but we could have traces much smaller. We could have traces much larger. And this probability distribution does allow for those extremes, but most of the data is concentrated around the mean width of 16 mil for about a 50 ohm trace, and then that mean length as noted. So what we do is we set up the probabilities, and then we just run through. We run through the number of points in a for loop, and each time through we generate a random width, random length, and we simulate and save it to a CSV. Well, we're putting it in a pandas data frame, and then save that CSV to the machine for future use. Now this procedure was replicated again, exactly the same procedure, but for 200,000 points. One set of 200,000 used for validation, and then another set of 200,000 used for test data that's unseen during the training process. So that's 1.4 million points in total. It took, excuse me, 2.25 hours or so to generate, so that's 5.7 milliseconds per point, and that includes all of the overhead. Now the field solver execution time itself, if you look at the average, that's about 982 microseconds per point. So some of the stats here. In terms of execution time, it ran anywhere from 871 at its fastest to 871 microseconds to 4.7 milliseconds at its slowest. So the mean there, 982 microseconds. I show at the right a histogram of the data. Note that I'm using a log y axis so that you can kind of see the distribution a little bit easier. But the minimum trace width is 0.3 mil, which is very, very tiny. That's not going to be able to be manufactured on standard feature sizes for printed circuit boards. And the max width is 500 mil. That's way beyond what you're going to be using for a regular transmission line for RF or digital design. In terms of length, we go from 0.136 inch, that's 136 mil, which is pretty small, up to 190 inches, which is very, very large. So this should cover the vast majority of PCB applications. Now, the next set of the code here just kind of moves some things around. I haven't touched on it yet, but I was going to be using Keras. I end up using both a little bit of Keras with TensorFlow and a little bit of PyTorch. So I was moving things into different arrays, tensors and such in this section of code, including training, validation, and test data. So next I had to build a model. Now from my experience before, I find that figuring out the right hyperparameters, and I didn't note this, but I am using neural nets in this example. I was very impressed with the presentation today about using XGBoost, and I'm absolutely going to look into that because the performance is amazing. In terms of neural nets, I know from my experience that determining which hyperparameter settings, number of layers, number of neurons, all of this stuff has been a major challenge. It's more of an art. So for this project, rather than using a guess, check, iterate flow that I've done in the past, I wanted to use Keras Tuner to search for the best hyperparameters. So here's the configuration for the hyperparameter tuner. I set up using a hyperband algorithm to search. I allow the tool to use anywhere from 2 to 5 hidden layers, anywhere from 32 to 512 nodes per layer, neurons per layer. For activation functions, I allowed linear, ReLU, LU, TAN-H, and soft plus, and then for the optimizers, the atom, SGD, AdaGrad, AdaDelta, and the N atom. And then for loss function, I also used 4 different options: MSE, MAE, mean absolute, the mean squared log, error, and then Huber loss. I included Huber loss here because on my the last paper, the 3D field solver neural net for the VIA, the Huber loss ended up being very good performance. So I configured the hyperband tuner with max epochs of 10, configured the data into some NumPy arrays, gave myself another Boolean to prevent myself from accidentally retraining a model if I didn't want to, and I ran the search. Now the search here took 3 hours, ran through 30 trials, and it gave me a best validation loss of 3.1 times 10 to the minus 5th MSE. So it sounds like it's really good. I thought I saw the end result of this hyperparameter search, and I was very excited. I thought it was going to be a phenomenal performing neural net. So I used Keras to create that model and to train it using those hyperparameters. And even though I had excellent MSE loss during the hyperparameter search, I was unable to replicate that performance in training. I never got better than an MSE of about 90, nowhere near the loss that I saw during the hyperparameter search. I did encounter the same situation with Kuros in that 3D full wave via work, reference 5 here. To be honest, I'm not entirely sure why this happened, why I couldn't replicate it with Kuros. But just like I did in that other paper, I went and I replicated it in PyTorch instead. So here I used PyTorch, wanted to configure the exact same neural net, same setup, and see how the process went. I created a normalization function here to scale the input between 0 and 1. This would allow me to use activation functions that have a max of 1, such as tan-h, which is something that I had done successfully in the past. I generated a sequential neural net model. So this is the same configuration you saw before with the min-max scaler, the normalization there at the beginning. I did make some minor changes to activation functions and added a soft plus at the end. Now, the reason for the soft plus at the end is that without it, I was seeing predictions that were negative. But these are all physical quantities of length and impedance, and these cannot be negative. So in order to sort of add a rectifying layer there, I added the soft plus. And so I ran through and I trained that on PyTorch. Another benefit of PyTorch is that it has good GPU support, easier to implement than Keras in my experience. I configured a PyTorch data loader so that I could adjust the batch size. I did modify the optimizer to be a resilient backpropagation algorithm. Experimentation with that showed a little bit better loss. And then another really important thing here, the very last 2 lines on this slide, I weighted the output. When I ran this situation, when I ran this neural net, I was noticing that electrical length would be predicted very well, but impedance was not predicted very well at all. So in order to compensate for that, I weighted the loss for characteristic impedance at 75% versus 25% for the electrical length. And that did help a lot. I should note that in some of the work that I did previously as the similar field solver work, my outputs were RLGC because you can compute characteristic impedance and other properties from RLGC parameters. And I tried a similar situation where I used a neural net with 5 inputs and 4 outputs, and I could never get it to work correctly. So in that case, I actually generated 4 individual neural nets, one for R, L, C, and G separately. So I was very happy that at least in this case I was able to use a single neural net model with 2 inputs and more than one output. So I trained that model. I ran it for 100 epochs. I did a separate validation step in the training process, output the status along the way. Now MSE was not nearly as good as I was hoping. We got down to 3.6 MSE loss, noticeably higher than that hyperparameter search as well. But the performance was adequate. I wish it were better. I wish that there was more time to work on iterating this system, this process, because it's not as precise as I was hoping it would be. It's not good enough to use as a design tool, as a replacement for a field solver. This plot at the right shows I don't have a traditional error percentage calculation, but I do have, for that unseen test data set, 200,000 points for each ideal or simulated value. I also show the predicted value on this scatter plot. So if this were performing perfectly, every one of those dots would line up exactly along that red line, 1 to 1, y equals x. Now, there are no negative predictions due to that final softmax layer, which is good. And also, you can see that there's worse performance at the extents, at the low end of the impedance scale and at the very high end. Along the middle there, it's quite a bit better. So like I said, that's a similar situation I've seen in previous work. Looking at performance of the electrical length, it is a lot better. You can see that the results line up much nicer on the y equals x line. And the reason for that, the reason I think, is that electrical length is almost essentially linear with physical length. We noted there's a little bit of a dependence on trace width, but it's very, very much more a linear electrical length to physical length calculation, whereas characteristic impedance, it's more of an inverse function. There's asymptote. As the width gets very, very small, your impedance is going to approach infinity, and as your width gets very, very large, your impedance will approach 0. And so as a result, I think that the neural net had more trouble with accuracy on that particular function. So the next step here was to save the model and look at some of the prediction time. So the model is only 324 kilobytes. And one thing, this is really one of the most amazing parts, is that in order to predict the 200,000 test points, I ran the prediction. I actually thought something was wrong. Now I am using the GPU to solve this, but it took total time to simulate all of this, 2.2 milliseconds, 2.3 milliseconds, which averages out to 11.4 nanoseconds per point, which is absolutely absurd, which is 82,000 times faster than the field solver here that we used in simulation. All right, so the next step was to do the same thing, but invert it. I created the inverse model. So I used the exact same neural net configuration. I just swapped input and output and retrained. Now, I did make one other change, which is that I modified the weights for the loss here. Went 90% on characteristic impedance, 90% on trace width and 10% weighting on the electrical length, physical length output. The MSE was a lot higher here. 67 was the final training MSE. And performance-wise, it looks better until you get to about 200 mil width, and then it deviates significantly from the ideal curve. Again, no negative predictions, and it never seems to predict an output value that's above about 250 mils. So there's definitely some sort of limitation going on there. In terms of performance for that physical length output, similar to what we saw before, it matches very nicely. So I saved this model. Computation time was on the same order. It was 11.98 nanoseconds per data point. Now I can't really compare this to a simulation per se because I didn't perform any type of reverse simulation synthesis. I only had the one set of simulated data. So I'd love to demo this. Okay, so I wanted to note I don't allow I create an application. I don't allow the user to input data that's outside of the middle 98% of the training data so that we can kind of avoid the really poor accuracy there. And so I have an image here showing the distribution of the data. So if in this user application, this console-based application, it allows for both analysis and synthesis. Accuracy is reasonable compared to line calc. So what we'll do, I will show the demo here. So I'm going to run it. And so the program asks if we'd like to analyze or synthesize. So to start out with, I'll do analysis, and we'll give a trace width of 16 mil, and we'll do a trace length of 10 inches. And this predicts that we have a Z0 characteristic impedance of 52.57 ohms and 516 degrees. Now I want to just jump back here to the slide at the beginning when we tested our function. So this was the same data that we used to simulate when we tested our field solver function. So we put 16 mil width, a 10-inch length into our field solver, and our result there was 51.9 ohm. Compared to the machine learning model at 52.57, and then we were getting 515.6 degrees simulated, 516 degree predicted. So I'm relatively happy with that. And we can show an example of the reverse here. I'll use those exact numbers actually. So we'll synthesize, and we'll use let's see, 52.57 ohm. And then electrical length 516.469. And this tells us that the trace width is 15.4 mil with a 10.019 inch trace. So we definitely see a difference in trace width. This is more than half a mil off on the trace width. It's only 19 mil off on a total 10-inch trace length. So it's reasonable. You can see it's getting very close, but it's not quite design worthy. And we can compare that, actually. We can compare that to line calc as well, and I'll pull that up right now. So we'll do the same 16 and 10,000. We'll analyze that. And line calc tells us 50.57, so about 2 ohm difference, and about 9 degree off, 507 degree. All right, so future work. Like I said, I'm super interested in this particular field. I'm really enjoying the research that I'm doing with Dr. Z on this. So I think there's a lot of opportunity to use this type of solver within a commercial tool like Cadence Sigrity, ANSYS HFSS, Keysight ADS. I've got large simulations that are taking many days to run. So one of the situations I'd like to see is if you take one substrate configuration, a lot of times you're doing a design, your substrate is unchanged, but your design process is going to take a long time. So if you could train a machine learning model on that particular layer stack, and then speed up your simulation afterwards, you've trained it on that layer stack, you know what the vias are going to look like. So even if training takes a few days or a few weeks, if each simulation then takes seconds to minutes, using machine learning instead of traditional simulation, you could shave weeks or months off of your design time. This faster turnaround time means that you can get feedback on changes to your design near instantaneously. So I'm looking to continue research in this area. So just as a quick summary, I do have the code available on GitHub, just a subset of the code because the training data is large, but it has the PyTorch models and the user application there if you wanted to test it out. So we created a neural net-based transmission line solver. It allows the designer to analyze characteristic impedance and electrical length from trace width and physical length and vice versa, packaged there into a simple Python script. And here is a list of all of the references that I used for this project. And that's it. Thank you very much.